Today we're going to finish off the study of the sampling and reconstruction process for how we turn continuous time signals into discrete time signals. We've already looked at the spectral effects of that, how the spectrum of an analog or continuous time signal is affected by the sampling process using an impulse sampling model. We've looked at the effect of aliasing, where the frequency content is moved to a different place in the frequency domain, or if a single sinusoid is moved to another frequency due to the fact that it violates the Nyquist criterion and is a frequency that exceeds half the sampling rate. In this last lecture, what we'll look at is some of the details and some of the practical considerations that go into the sampling process, what kinds of things we have to do in the real world to prevent things like aliasing, and what the reconstruction process looks like, how it is we take these digital samples and turn them back into analog signals. Now, so far we've only talked about the sampling process. We haven't talked about reconstruction. Sampling, we're talking about the analog to digital conversion, going from continuous time to discrete time. Reconstruction, we're talking about the opposite, going from discrete time signals back to a continuous time signal. The sampling usually involves several steps that we'll look at: filtering to prevent aliasing, sampling that we've already modeled, quantization of the signal into integer kinds of values, and encoding that into a binary pattern. Reconstruction is the undoing of those processes. It's decoding the binary number and turning it into an analog voltage using some kind of digital to analog converter, and also in some kind of anti-imaging filter or reconstruction filter that lets us remove the periodic spectral copies that come from the sampling process, that smooth out the digital to analog converted signal and provide us an analog or continuous time signal. As we studied already, the sampling process creates multiple copies of the spectrum of the incoming signal, where those multiple copies are centered on every integer multiple of the sampling frequency. And so we now understand that if we reduce the sampling rate, we've also reduced the Nyquist rate, and the spectral copies in the digital frequency domain will show up more closely, less spaced, more close together. Whereas if we raise the sampling rate, then Fs moves out, the spectral copies move further apart, and we have more distance between each copy. Looking at this from the continuous time frequency domain, and if we compare the sampling at two different rates, we again see at a higher sampling rate the spectral copies are further spaced apart. But if we look at it in terms of digital frequency and keep our axis the same, although the same effect is happening, to us it appears as though we've kind of compressed or narrowed the spectrum of the original signal, where that's not actually what's happened in fact, but in fact the analog signal, the sampling rate, Fs, is always a digital frequency of 1, and so what analog frequency and what analog frequency range that corresponds to the digital range of 0 to 1 is expanding when we use a higher sampling rate. So why might we consider doing this? Well, by putting more distance between the spectral copies, it makes it easier for us to extract just the center one that we want when we go through the reconstruction process. It also gives us a higher Nyquist frequency so that we have less likelihood of having aliasing in our signals when we're doing the sampling process. So what are the problems with ideal sampling and reconstruction? What are some of the practical things that come in to play when we sample real-world signals? Well, first there's a theorem, the time bandwidth theorem, that says if I have a finite length signal, it cannot if it's finite in length in the time domain, it can also not be finite in width in the frequency domain. And so a finite length time signal cannot be band limited. And most of the signals that we'll be looking at are finite length, or at least we'll be looking at a finite number of samples of them. And it's also true that most signals must be band limited to this Nyquist rate, or fs over 2, or else we're going to have aliasing. And so what's required to get good sampling results to prevent aliasing is, well, we definitely need the amplitude spectrum of the signal that's coming in to be negligibly small for any frequency above the Nyquist rate, because that's the part that's going to alias. How small does it have to be? Well, practically, if you think about this, we have these discrete levels that we're going to be digitizing our signal values into. And so if I can get the amplitude of any signal that's going to alias to be smaller than 1 A to D count, or 1 bit on the A to D converter, then I don't really see it in my digitized signal. Now that could be pretty small, but that would be the ideal case. If I can keep anything that's going to alias to be less than 1 A to D count, I would notice it in my discrete time signal. The problem is that we really don't necessarily know what the bandwidth of an incoming signal is. When we design a system, we'd like to know, so that we can choose a sampling rate to set the Nyquist frequency so that we don't get aliasing. But sometimes we're getting signals from sensors or from other unknown sources that we don't know what the upper boundary is going to be on their frequency content. And if we have, even if we do know the frequency spectrum of the signals coming in, we might also couple in high frequency unintended into our signals. And if that happens, we're going to get that high frequency noise will alias and mess up our digitized signal. So one common approach to how we deal with this is to place a filter known as an anti-aliasing filter in front of the analog to digital converter, so that one that's able to remove, well, preferably all, but at least most of the signals that are at frequencies above the Nyquist rate, so that there's very little signal left to alias. The other option that we have is to raise the sampling rate. Use a higher sampling rate so that the upper boundary of what's going to alias goes higher and higher and higher, and hopefully gets high enough to encompass all the frequencies that we have actually coming in on our signal. In reality, most digital signal processing systems will actually use both of these approaches. To be safe, most systems will put anti-aliasing filters in front of the A to D converters, and they will also tend to sample at a rate that's not exactly at the Nyquist frequency, or twice the Nyquist frequency, but will sample at a higher rate to give themselves some extra headroom. So if we look at a signal in a case of aliasing in the frequency domain, if I have an incoming analog signal coming into my sampler and that has some frequency content above the Nyquist frequency Fn, which is half the sampling rate, and then we do the sampling process and make the spectral copies, we know that those part of the frequency domain, the part of the spectrum of our incoming signal that exceeds Nyquist rate, is going to intermix and cause overlapping and aliasing. If we put an ideal anti-aliasing filter in front of the sampler, one that's a low-pass filter with a very sharp cutoff, and that cutoff frequency will eliminate every signal at any frequency above the Nyquist rate, as shown in the frequency response in red here. Then when we put that same signal in, the anti-aliasing filter removes those parts of the frequency content that will alias and leaves alone the part that won't. Then when we do the sampling process, we don't get any overlap of the repeating spectra, and we have a ideally sampled signal that we can reliably recover without aliasing. Now, What does an anti-aliasing filter look like in the frequency domain? Well, ideally, we would love to have a filter like this, an ideal low-pass filter that has a gain of 1 in the pass band, has a gain of 0 in the stop band, and we set the cutoff frequency right at the Nyquist rate at fs over 2, and have a very sharp cutoff. So we want flat pass band with a gain of 1 from 0 to the Nyquist frequency. We want that really sharp cutoff at the Nyquist rate, and we want complete attenuation, and we want 0 response at all frequencies above that. Now, this is a picture of an ideal low-pass filter. Turns out I cannot make this filter in the real world. It would be an unstable filter that would be a very, very, very high order, and also would be non-causal. And so we can't really make, with physical devices, a filter that has this particular frequency response. Instead, we can make a practical low-pass filter that has certain compromises in that frequency spectrum. Most notably, it's going to be some amplitude distortion, some ripple in the magnitude response of the filter in either or both the pass band and the stop band. And particularly the roll off the cutoff at the cutoff frequency is not going to be a sudden brick wall, but there'll be a much more gradual change from the pass band to the stop band. How sharp that cutoff is depends on the order of the filter. The higher the filter order, the sharper that transition will get. But the higher the order of the analog filter, the more op amps, the more components I need to build that filter. And a practical filter will also have not just 0 response in the stop band, but it will allow a certain amount of the signal through, even though it's in the stop band, because of ripple in the response. And so some still residual amount of the signal is going to alias. Here's a comparison of the frequency response of several practical anti-aliasing filters. These were all made in the Butterworth configuration. If you're familiar with analog filters, there's a few standard types, Butterworth being one, Chebyshev being another, elliptical being a third. Butterworth filters are nice because they have a monotonic response. They have very little or no ripple in the pass band and stop band, but they do have fairly slow transitions from pass band to stop band. And so the comparison curves here show you for 4 different filter orders, for a third order filter, fifth order, seventh order, ninth order filter, what kind of transition width you can get between pass band and stop band. And you can see even with a ninth order filter, which would require quite a number of components to build, we still have a fairly gradual roll off in the between the pass band and stop band. So what's actually done in the real world is to use a not so high order analog anti-aliasing filter, because that's much less expensive, and put that in front of the A to D converter. And then we'll tend to oversample. We use a higher sampling rate than we might have needed if there wasn't aliasing, so that we have some extra headroom, if we have some extra room between those spectral copies, so that we can use a lower order filter and still have it work effectively. Now, so oversampling can be taken to some pretty strong extremes. In a typical case, we would use about a 4 times oversampling to give ourselves a lot of headroom. But depending on how critical your application is and how much you can and can't tolerate aliasing, and perhaps if you're also part of a control system, you might use a much higher oversampling rate and actually sample at 10 times the rate that you might predict that you need from the highest highest frequency that you expect to have in your input signal. Now, if that sampling rate is too high, then for the rest of the system to sustain, because we would need processors that could process those samples fast enough, things like that downstream that might get more expensive, then what's sometimes done is a kind of an interesting combination of filters where we'll use a an inexpensive low-order analog anti-aliasing filter. We'll use a very high-speed analog to digital converter to get a very high sampling rate. And then we'll actually add in a digital filter, a fairly high-order digital filter, to take those samples and remove any alias signal, and then actually downsample the result to a rate that the rest of the system can sustain. So here's what that looks like in the frequency domain. The solid shapes shown in this would be perhaps the frequency content of a signal that we're going to want to sample. And the omega n is the Nyquist rate for this main signal, but above that signal we see it has a little bit of noise, some high frequency noise. Above that is shown a frequency response for, or magnitude response for a fairly low order anti-aliasing analog filter. So it's flat in the passband and the part that we want to keep, but notice it rolls off very gradually above the Nyquist rate, whereas we'd really like that to be much sharper. But because it's a low order filter, that's the kind of slow roll off that we get. Now if I run that analog filter through, or excuse me, analog signal through that low order filter, here's the spectrum of what's going to come out. We still have noise, we still have signal above the Nyquist rate. We've done a little bit of good work there in pushing down the high frequency noise at the very highest frequencies, but there's still some residual noise above the Nyquist rate that might alias if I choose too low of a sampling rate. So if I choose the particular one shown, we see we would have some, that aliasing would in fact happen in the noise part of the spectrum. But if I choose my sampling rate wisely, then only the part of the noise that only the part of the signal that's above the bandwidth that I want to keep in my signal, the triangular part, is aliasing. So I go ahead and let the noise part alias, but make sure that my good signal doesn't alias. In that case, then we have to choose a sampling rate that puts the Nyquist frequency at the point shown here. And so we would use, as shown in this filter, a very simple anti-aliasing filter because it's inexpensive. It has a very low roll-off and only a little bit of in-band attenuation, so we don't distort things too badly. And then go to a very high sampling rate. Follow that high sampling rate with a digital filter, a digital anti-aliasing filter that might be less expensive to implement than the analog one, and then downsample. And by downsample, we mean if you've sampled originally at 10 times the sampling rate you needed, then when you downsample, you would throw away 9 out of the 10 samples. You would keep 1 out of every 10, and that would reduce the total number of samples you had. That would effectively cut your sampling rate by in 1/10. So what happens then with that filtered signal is we would put effectively a brick wall, an almost ideal digital filter to process it that picks out just the spectrum of the original signal part, well, the part that we wanted to keep originally, and we would have put a high order digital filter to extract that. And then the noise is gone, and even though it was aliased, and then when we downsample, it spreads that spectrum back out to the Nyquist rate of the new sampling rate, and we've got a undistorted, alias-free spectrum. Here's an example of the kinds of filters and actual frequency responses of filters that might be used in this kind of setup. Here at the proposed Nyquist rate of fs/2, we'd use a low-order Butterworth filter that only begins to roll off a little bit at the intended Nyquist rate, but that does roll off at higher frequencies. Then we would digitize at a very high sampling rate and use a very strong anti-aliasing digital filter like the one shown in the right here, and combine their filtering abilities to make sure that we don't have aliasing and don't pass noise into our sample data system. And here's a block diagram of how that works. Um, if we were just using the anti-aliasing filter, we would be in a setup like shown in the top, use a fairly high order analog anti-aliasing filter, maybe a little bit more expensive, and then do conventional sampling and analog to digital conversion. Or as this other approach that we've talked about, you can use a lower order anti-aliasing filter, oversample by 4 to 10 times, do the analog to digital converter, which would obviously require a faster converter, implement a high order digital anti-aliasing filter using some high speed digital electronics, and then downsample by a factor of 4 to get back to the original intended sampling rate. Both of these approaches could work. Now let's look at what the signal looks like going through some of the stages of analog to digital conversion and sampling. So if we have an input signal, maybe that's carrying a little bit of noise on it, and run that through our anti-aliasing filter. The anti-aliasing filter is a low-pass filter, and so it's a smoothing filter that eliminates some of the high-frequency variation in the signal. Now, it's not unusual to precede an analog to digital converter with a sample and hold circuit. A sample and hold circuit that would grab a sample of the signal and hold the value of the output to that one sample signal. So keeping things constant over each sampling interval so that the A to D converter is presented with a constant signal to convert to digital form. This is often necessary to reliably do the analog to digital conversion process because of the way A to D converters work. If you're changing the input, then that may confuse the digitizing process, and it may come up with the wrong value for what level the signal is. Beyond the A to D converter, we have the sampled signal. The sample values actually is usually as binary numbers, one for each sample period. And again, the sampling process is actually a two-stage process. First, we have to do the sampling, and we've been modeling that, taking the analog signal and turning it to digital samples. But we also have a quantization process where we're rounding off the voltage level of the input signal between quantized levels that we can turn into digital numbers. That quantization process introduces some error into the signal where we're not giving it an exact representation of the voltage level of the incoming signal, but we're rounding it off, either rounding it up or rounding it down to the nearest quantization level. That rounding process therefore represents an introduction of a little quantization noise. Here's the way we typically specify an analog to digital converter chip. So if we show this a transfer function of an analog to digital converter chip, the independent axis, the x-axis here, is the voltage applied to the A to D converter. The vertical axis is what quantized level, what binary value comes out of the A to D converter, depending on what voltage level you have going in. And the transfer function is a staircase like this, that there's some range of input signals, some range of voltages that result in the same digital output, the same quantized output. The width of that range we use a delta to describe. That tells us the resolution of one bit in the analog to digital converter, meaning that every time I change by one bit or one count in my output, it represents this width, this much of a voltage change on the input signal. The maximum minimum voltages that you can convert to digital form are shown here, and the difference between them is called the full scale range of the analog to digital converter. There's usually a limit, an upper and lower limit to the voltages that can be reliably converted to a digital form. If you, for example, put in a voltage that's too high, that's above Vmax in this case, well, there's no additional numeric values to increase to, and so any signal above Vmax is always digitized to the highest possible level. And so there's a form of clipping going on here. Same thing if you put in a signal that's too small in voltage or too far negative, there's a boundary below which all signals that are less than that will have the same output. And so there's, again, clipping in that direction as well. Now, the resolution of the converter, then, this delta width, is nothing more, can be computed mathematically by taking the voltage of the full scale range and dividing it by the number of different steps we have in our converter. And since these are usually digital converters that convert things to binary numbers, the number of quantization levels we have is usually some power of 2. For example, as shown here, I have a 3-bit converter. I have 3 different bits that can represent the different quantization levels. That means I have 2 to the 3 or 8 different quantization levels. And so if my V min was minus 5 volts and my Vmax was plus 5 volts, I'd have a full scale range of 10 volts. And the resolution then would be 10 volts divided by 8 levels, or that many volts per bit, or volts per level. Now, in terms of how this is done in hardware, how do A to D converters work internally? There is actually a number of different styles of A to D converters. You may have come across some of these already. A common kind is called the digital ramp A to D or delta encoded A to D converter. And showing it simply in block diagram, we have a comparator where the signal that we want to digitize comes in one side of the comparator. On the other side of the comparator is a digital to analog converter whose digital input is given by a counter, a binary counter. So as that counter counts up, the digital analog converter puts out a successively higher and higher and higher voltage. What happens then is we apply our input voltage to this converter to one side of the comparator. The binary counter again drives the D to A converter, and the output of that goes to the other side of the comparator. To start a conversion, we reset the counter to 0. The digital analog converter puts out essentially 0 volts, and that's compared with the input signal. If the input signal is bigger than 0 volts, the comparator stays tripped, tells the AND gate to tell the counter to count up another step. And then it does, and it keeps on counting up until the output of the digital to analog converter, as it steps up, as the binary counter increases, the D to A converter keeps stepping up its output voltage, and that continues until the comparator trips, because the output of the D to A converter is now higher than the input voltage coming in. And when it trips, that stops the counter, and the number that's on the counter output is effectively used as the binary representation of the voltage level that came in. So it's a pretty clever approach to doing analog to digital conversion. It's actually pretty straightforward to design. So it's very inexpensive. It's very accurate. You can get 16-bit or better resolution in this kind of converter. 16 bits would mean you have a converter that has 2 to the 16th or 65,536 different levels, which is very good resolution. Problem is it's pretty slow. You have to clock through a lot of possible counts before you find the right one, and so the conversion time, the time it takes to take one good accurate sample of your input signal, is fairly long. A more common and faster approach to doing analog to digital converter is similar, but a little bit more clever. It's called a successive approximation A to D converter. Again, I have a D to A converter driving one side of a comparator, and my input signal driving the other. But this time, instead of just stepping through a binary count and making a stepladder kind of input signal with the D to A converter to compare with, the successive approximation converter instead does a binary search in essence for how it's going to find what the actual output or what code the input level is. So we start the converter first by setting the most significant bit of the A to D output count to 1. So we're basically testing should the most significant bit be set. The D to A converter puts in basically a half the full scale range output in response to that, and that's compared to the input signal. If the input signal is smaller than that big jump, then we say, nope, that bit doesn't belong there, and we set it back to 0. If the input signal is still bigger than the amount that the D to A converter put in, then we keep that one there. Now in this case, the DAC, the D to A converter output exceeds the voltage on the input, so we wouldn't keep that most significant bit equal to 1. So we'll set that to 0 and then try the next bit. And when we set the next bit to 1, well, we get a value that's still below the level of the input signal, so we keep that one. Then we go to the third bit and we set that one high, then add together the 2 bits worth of output, and we're still not high enough to match the input signal. So we keep that bit and then go on to the final bit, add that in. When we add that in, we're still a little bit below, so we keep that. So again, it's kind of like a binary search. We're testing each bit one bit at a time, see whether it should be on or off, and accumulating the proper output signal. So in this case, it's also a fairly inexpensive and very accurate kind of converter. Again, you can get 16-bit A to D converters of this style. The thing about this one is I don't have to go through, let's take an example. If I had an 8-bit converter, with the other style, I would have to perhaps step through 256 different levels to test before I knew which one was appropriate to use. In the successive approximation converter, I basically just do one test per bit. So if I had an 8-bit converter, I would need only 8 tests, 8 cycles to get the answer. So the number of clock cycles it takes to do a conversion in a successive approximation converter is exactly the same as the number of bits we're trying to resolve. So these are much faster. The fastest A to D converter is known as a flash converter. Here I have a whole stack of comparators, and I have a large voltage divider network set up feeding the negative sides of all those comparators. The positive side of all those comparators goes to the same input voltage. The resistor ladder we have basically applies a different voltage, a successively higher one to each of those comparator inputs. Then what we're basically doing is comparing the input to all of those different possible levels and finding which one is it that changes from that the input voltage is greater than. And so each of these stack of comparators puts out what's essentially a binary code, a thermometer code, where at some point we go from the transition of a 1 because the analog input's bigger than the resistor ladder voltage to a 0 where now the resistor ladder voltage is higher than the input voltage. And we can use a priority encoder to convert that thermometer code into a binary output. You've probably encountered priority encoders back in CPE 133, so hopefully you know how they operate. This kind of converter is extremely fast. You only have to wait for the time it takes for the comparators to respond before you have an output, basically. So these are the fastest style. You can get up to a gigasample per second or more, that being a billion samples per second. Problem is that these are very, very expensive. Um, you have very limited resolutions. 8-bit converters are about the highest you can get in right now in a flash converter, because 8 bits requires not 8 comparators but 256 comparators. And then because these are analog comparators, you have to worry about component matching and making sure that your resistor network divisions are completely accurate. So these tend to be very expensive, very large, consume a lot of power. But if you have an application that requires super speed, if you've got to have those gigasamples per second, like if you're making a super high speed oscilloscope, or a very high speed piece of digital signal processing equipment, then this might be your only choice. There are other hybrid kinds of approaches that people have come up with, one of which is a pipelined ADC, which is effectively a small flash converter or a number of small flash converters where we break up the job of resolving a higher resolution number using a series of successive flash A to D conversions. These are much less expensive than a flash converter. It uses a small flash, a couple of bits worth of flash, but reuses them to resolve the conversion in a piecewise kind of way. So because you're doing this sort of serially, that increases the time, not quite as fast as a flash, um, but gives you some reasonable resolutions. You can get now between 8 and 16 bits resolution with this style and still very high speed. A very common style that's come into use, particularly in audio applications, is a sigma delta oversampling A to D converter. These are fairly complicated to understand, and you have to really understand about noise theory and um, the effects of oversampling on the spectrum and some other details that are beyond the scope of our course. But we can understand some of the basic principles involved. The first principle is that um, if you can have a 1-bit analog to digital converter that gives you actually the same resolution as a 4-bit analog to digital converter if you use a lot of oversampling. If you wanted to use that approach to get a 16-bit resolution with a 1-bit converter, you'd have to oversample by a huge amount, which is really not realizable. But there are certain tricks you can play that let you use this approach to using oversampling in place of resolution to gain effective resolution. And that's how these particular A to Ds work. Now, if you think about why is this so helpful, well, a 1-bit A to D converter is pretty simple. It's just a comparator. Is it above a certain level or not? And so that's very simple to make. And here if we can do that, make that decision, is it above or not, a lot of times really, really fast, turns out that we can actually effectively resolve an input signal into more levels than just the one. Now, those delta sigma converters are pretty slow, but they're very inexpensive, and so that's why they come into vogue for things like music players and that sort of thing. Of all those types, this chart shows you kind of what the trade-offs are between speed on the vertical axis and resolution on the horizontal axis. The delta sigma converters kind of live in the realm of very high resolution, very slow converters. Successive approximation converters bridge between low and high resolution at kind of moderate sampling rates. Pipelined converters would be a little faster than those. Flash would be the very fastest, but very low resolution. And again, the idea of a pipeline converter is to try to bridge the gap between successive approximation and flash converters in terms of speed and resolution and cost. So that's been a lot of what goes on at the front end of our sampling system. We talked about anti-aliasing filters and what they're for, how they could be implemented. We looked at the analog to digital conversion process, what kinds of converters you might encounter, what the different specs are in that, why we might use some oversampling for that. Now we want to talk a little bit more about this other process, the reconstruction, the digital to analog converter process, how we take a discrete time signal and make it continuous time. In terms of architecture, what's inside of a D to A converter? Here's this pretty standard kind of drawing. You can think of a D to A converter as a bit of a summing amplifier where my binary bits come in on the left and they go into a weighted resistor ladder network that each bit provides a different amount of voltage, a different proportional amount of voltage through this amplifier on the output. So the most significant bit would create a larger voltage, twice as big as the next bit below it, using this configuration. And so the D to A converter's amplifier there is a summing amplifier that takes these weighted voltages from the binary input and converts them into a single voltage on the output. Again, what's going on spectrally when we take our analog signal, sample it with impulse sampling, and create those spectral copies. On the other side, for reconstruction, we want to get rid of those spectral copies. And so we interject a reconstruction filter, again a low-pass filter, whose ideal frequency response would mimic exactly the ideal frequency response of the anti-aliasing filter on the front end of the system. It would have a flat pass band that would go from 0 up to the Nyquist rate. And in the case of our sampling model with impulse sampling, we said that the sampling process scales our signal with a gain of 1 over T sub s. Yeah, so using that model, we would want to undo that gain change by using a reconstruction filter that had a gain of T sub s on the output. And so that's what we see in this middle diagram here. The amplitude is T representing T sub s and goes from minus the Nyquist rate up to positive the Nyquist rate. Then if we pass that repeated spectrum signal on top through that low pass filter in the middle, what comes out is what's on the bottom, and we're back to our original amplitude signal. We get back our unity output, and any spectral copies are eliminated. So the ideal reconstruction filter is again an ideal low pass filter, which actually I can't make in the real world. Its frequency response would be 0 above the Nyquist rate and T sub s between DC and the Nyquist rate. In terms of what that would look like for its impulse response, we'd have to take the inverse Fourier transform of this shape, which is effectively a rectangle, and the rectangle's inverse transform is a sinc function. So we would expect the impulse response of this ideal reconstruction filter would be a sinc function, specifically sinc of T over T sub s, where Ts is our sampling interval. If that's our impulse response, then what's going to come out of the reconstruction filter then? Well, if we look at that in the frequency domain, we know we're going to multiply the spectrum of our input signal by that rectangular function low pass filter characteristic. In the time domain, we would look at that using convolution. So we would convolve the input signal with the impulse response of our reconstruction filter. We said the input signal is modeled with a series of delta functions, And so we have the sum from n equals minus infinity to plus infinity x of n delta of t minus nt sub s. That was our model of the impulse sampled signal. We're going to convolve that with the h of t, the impulse response of our filter. And when we convolve something with an impulse, we get that same function shifted over to where the impulse is. So the result of that convolution would be the sum from of n equals minus infinity plus infinity of x of n h of t minus n t sub s. And we know what that, we derived what that impulse response is. We know what h is. It's a sinc function. And so we have this final mathematical model for what the reconstructed signal is going to look like. If we input x of n delta sampled signals, put them in an ideal low-pass filter with a sinc function impulse response, we're going to get this last equation where what comes out, the continuous time signal, is the convolution of those sample values for the output signal with a sinc function. Let's look at that graphically. So here on the left, we have a series of output samples coming from our digital signal processing system. And we'll use our impulse model again. So those are a series of impulses with different weights, where their weights are the sample values. The shown on the right is the reconstruction filter's impulse response, a sinc function. And we're going to convolve the input sample, or excuse me, the output samples with that reconstruction filter response. And when we convolve things with impulses, well, we make copies of them, centered where the impulses happen, and scaled by the weight of the impulse. So that first impulse, the output going into our low-pass filter, would produce a sinc function centered where that impulse was. The next one would similarly create another impulse, another sinc function centered on it and scaled by its sample value. The third one would do the same, and so on, and so on, and so on. So we have this series of sinc functions that would be all added together to get the total response of the filter to that signal. And that sum of sinc signals would in fact give us a analog continuous version of our sample signal that matches the sample values at their instances and interpolates perfectly between them the intermediate values that we need to make an analog signal. And so if we could create an ideal low-pass filter, it would be the perfect reconstruction filter. It would perfectly interpolate between the values of those samples to create an analog voltage that represents the one that we want from our output samples. So we would, again, for ideal reconstruction, we're going to we'd like to connect the dots between the heights of our sample values, and that could be done by convolving it with this ideal impulse response of an ideal low-pass filter. It would do that interpolating for us exactly correctly. Now, unfortunately, again, the same story we said about anti-aliasing filters, I can't make in the real world an ideal low-pass filter. I would need an ideal brick wall filter, and I just can't make those. So practical systems don't use ideal filters. They can't. But often we'll use at least a zero-order hold block or a zero-order hold followed by a low-pass filter. What's a zero-order hold? Well, it's kind of the opposite of that sample and hold that we had on the input. On the zero-order hold, if we put a single sample value in, like from our x of n signal, the D-to-A converter is going to convert that to an analog voltage and then hold it at that same level for the whole sampling interval until the next sample comes along. And then it will change abruptly to that new sample level and hold the output at that until the next sample comes along, and so on and so on. So we end up with kind of a staircase-shaped output for our D-to-A converter. Now that's not exactly the most ideal signal, but it's close. It's kind of on the right track for creating an analog representation of our digital signal. What's typically done then is we'll run that output through a low-pass filter to smooth it out a bit so that we get a better looking reconstructed signal. Now, if we could make an ideal filter, we would, but we can't, so we use a reasonably inexpensive low-pass filter to kind of just smooth out the edges. Now, we can look mathematically at what's going to be the effect of not using an ideal reconstruction filter, but using this sample and hold, or the zero order hold kind of D to A converter instead. And we can do that using techniques that we already understand from EE328. Again, we can describe this zero order hold function as having an impulse response shown here. So if I put in some sample value at time t equals 0, this system is going to hold that sample value for one sampling interval t sub s. And if so the impulse response of this filter will have a height of 1. If I put in a sample value of, say, 3, then that 3 value would be convolved or scaled my impulse response for one period. In order to see what this is going to be the result of processing those digital samples through a filter with a zero order hold style response, we would convolve that response, that H0, with our impulse sampled digital signal, as shown here. And again, we'll get the convolution of our signal, our sample values, with these rectangle functions. In terms of what that looks like in the frequency spectrum, well, we would take the spectrum of our signal, our x of f, and we would multiply it by the Fourier transform of this zero order holds impulse response. And again, since we have a rectangle function for our impulse response, its frequency response, its Fourier transform, is going to be a sinc function, as shown here. So the frequency response of this sample and hold function is a sinc function. It's a scaled sinc function. We have a 1 over fs scale factor. We also have this exponential term, e to the minus j pi f over fs. That represents a delay, a time delay, half the width of that sampling interval. In terms of how that will affect our frequency response, well, that's not going to affect the magnitude response at all. That's going to only affect the phase of the system, the phase of the frequency response. So graphically, seeing how a signal processed with a sample and hold reconstruction would look like, at the top of this diagram we have an analog signal whose continuous spectrum looks as shown. And when we sample it, we get the second line where we get all the spectral copies. Now, again, we would prefer to use an ideal low-pass filter to pick out just the center triangle. But instead, if we use a sample and hold kind of D to A converter, the frequency response is what's shown in the next two lines. The magnitude response at the top having a sinc function kind of shape. The fourth plot there is the phase function of that filter, of that sample and hold function, which has a straight line linear phase response. We can ignore that for the moment. That's just a time delay. If we look at the amplitude response, though, if we multiply the sampled signal, the B spectrum in line number 2, by the frequency response, magnitude response of the zero order hold in line 3, or C there, we get the bottom line, the D magnitude spectrum of the output signal from zero order hold. Notice we kind of have the triangle, center triangle, that we wanted to keep. We've actually distorted it a little bit because we have a sinc function, a rounded shape in the middle, not a rectangular shape. And notice where some of the spectral copies are, we haven't completely eliminated them. We've kind of pushed them down and suppressed them a lot, but there's still a little bit of them there. So This is non-ideal. It's a kind of reconstruction method, which if we follow this up with another low-pass filter, we can get rid of the rest of those spectral copies. But notice we have distorted the main spectrum a little bit. What do we do about that? Well, if it's really critical, it's not uncommon for systems to try to compensate for this using another anti-imaging filter, either an additional analog filter or more likely some pre-processing done on the digital signal before it's put out to effectively change it with this sort of inverse filter that reverses the effect of the distortion from the zero order hold filter. So notice where previously the zero order hold filter had a uh, concave downward kind of shape in the center, the compensating filter has a concave upward shape that together with the other, the total response would be a flat response. And so this would be the shape of a filter that might be used to compensate for distortion from a zero order hold. But again, this may or may not be done. It depends on how critical the signal processing is in the system that you're using. So again, the whole process of digitizing, it's more than just an analog converter and D-to-A converter. Up front, we have to have some kind of anti-aliasing filter to make sure that the signal coming in doesn't have frequency content that's going to alias or hasn't picked up noise somewhere that's going to alias. So that's a low-pass filter that band limits our input signal to the Nyquist rate or less, then followed by an A to D converter, which requires sometimes sample and holds, has an actual converter that does two things, does a sampling operation that we've modeled with an impulse sampling model that gives us one sample every t sub s, and that sample is then quantized to a binary level and encoded as a binary signal. That then goes to our signal processing system that does its magic. What comes out then is still a discrete time signal that we have to turn back into an analog signal by reconstruction. Usually that would go through a device called a D-to-A converter that would decode the binary number, and using a weighted amplifier system would come up with an analog voltage, would tend to hold that same voltage for each t sub s period in a zero order hold kind of mode. And we would follow that up then with some kind of anti-imaging filter that would be a low-pass filter. It'll smooth out the jagged D-to-A converter results and provide something closer to an ideal reconstruction. Now, to give you an example for a real-world system and some of the parameters that it uses in its sampling and reconstruction system, you can think of compact disc audio, which is two channels, left and right, so it's always processing two signals. The highest frequency we expect it to have is about 20 kilohertz, the upper range of human hearing. The A to D converters for digital audio for compact disc recording uses a sampling rate of 44,100 hertz. So the Nyquist frequency for that sampling rate is 22,050 hertz, which exceeds the 20 kilohertz that we expect the maximum frequency to be in audio signals. In terms of quantization, compact disc audio is a 16-bit numeric values that they use, so that means there's 65,536 different levels. For reconstruction, to go back to the analog world, compact disc players often use a bit of oversampling on that side. They use a 4x interpolated delta sigma 1-bit D-to-A converter at a very high sampling rate, which is then downsampled and filtered with a anti-aliasing filter, or excuse me, anti-imaging filter. So that concludes our study of sampling and reconstruction. Next week we'll be moving on to looking at discrete time systems instead of discrete time signals. And please check the schedule for the course to look for homework problems to work associated with this information. And we'll see you next week.